Okay, this is lecture 20. Let's start. So, are there any questions on what I did last time? We stopped somewhere in the middle of something, so we'll just continue it. But if there are any questions, you're always free to ask. So, where did we stop last time? We were trying to understand how to evaluate the path integral for the case of a free scalar theory. Free scalar field, just to be definite, and we came to this following answer, which is that, okay, I've tried to correct some i's in my notes, but I think I have not done a complete job of it. Yeah, this is proving quite tedious. Yeah, I might not get the i's correct, but I think the general idea is that z is e to the 1 by 2 integral. So I'll try to correct these i's before I upload the notes for today. The problem is to decide whether O contains the I. I think in this form O contains the I, and I think this plus is correct because originally we had e to the minus half phi O phi, but when we complete the square we always get e to the plus to compensate for some extra term, and so I think this is actually correct. And the rule is that to calculate integral d phi of x1 up to phi of xn e to the is, I just need to write this as minus I del by del j at x1 minus I del by del j at x2 and keep going. Of zj, and after I have done all that differentiation, I said j equals 0. So zj is evaluated to be this. What was the definition of zj? I should also write. So this is what it's defined as, and for the free theory, this is what it becomes. And then I can calculate these correlation functions like this, and then if I want to have them normalized, I should divide this by the same integral with e to the is, and here I just have to divide by z of 0. This thing is z of 0 by definition. So now that we have this form for it, we can actually do the calculation for the free theory. And maybe I should have said this form really doesn't depend on it being a free theory. This is always true, because whatever is the s of phi, I just have to add j phi, and then when I differentiate in j, I pull down phi, so I always get this object. So that's general, but now let's evaluate it for the free theory. And the first thing we find is that, okay, I need some notation for this numerator quantity. Okay, or let's we have a notation for the whole thing. This whole normalized object we had called phi, the correlator phi of x1 up to phi of xn. Okay, that includes the normalization. Okay, so let's start with the this is called n point function. So let's start with 1 point function. So for this, we have to differentiate this quantity in J that pulls down O inverse J. It does it twice because of this. There's a half here, but there are two J's that I could differentiate there. And so I will get O inverse J and times Zj again. And this whole thing will be evaluated at x1. And there may be an I, or there might not be an I. This I'm not sure. I think in this notation there's no I. But
minus I, right?
Minus
we are
I.
doing minus I del by del J.
No, that I'm doing, that's because of this I. But whether there's an I in O.
So if I is absorbed in O, then there is none. Like in the free theory form.
Yeah. So I think I is should be absorbed in O. Then this is correct. You're saying this is not correct? There's some more I needed?
No.
Because this term is I J phi. So then this minus I always is to kill the I. And del by del J deletes the J. So it's this. But now I have to put J equals 0. But there's still a J sitting here. So this is 0. So in a free theory, 1 point functions are 0. Next one, phi of x1, phi of x2. Well, I can just proceed with this result and differentiate once more. Before I said J equals 0. If I differentiate this once more, I can either differentiate the J sitting in Z or the J sitting outside. But if I differentiate the J sitting in Z, then again this will vanish when J is set to 0. So I better differentiate this J and only then set J to 0. When I set J to 0, this will become Z of 0, but that's divided out, so it cancels. So I'll simply get O inverse. And now we have a nice sort of physical result. This operator O, which was quite abstract and which we were hoping we can invert, is actually nothing but the 2-point correlation function of the field. And that's why I have normalized it like this, so that it's exactly the right 2-point correlation function. Yes.
So can we use this to, like, for some theories we don't have O inverse?
Yes.
We can use that to show that the theory is wrong because O inverse should always exist and be equal to this.
It may not be that the theory is wrong. For example, in gauge theory, O inverse doesn't exist. But it's not that the theory is wrong. In fact, it describes all of nature as we know it, so it better not be wrong. What is wrong is that we can't do this stuff naively as we have been doing because of gauge invariance. It certainly means we are doing something wrong, but I would not blame the theory as you want to do. I would blame ourselves. If we try to do this, we'll end up with an O which is not invertible in a gauge theory, and we have to do something more to fix it. So the rules for evaluating path integral are different when there is gauge invariance. That's actually the next topic I was planning to do, but I started feeling today that this everything I'm doing is so super abstract that I should first do a few concrete things, and when we need it, we'll discuss path integral for gauge theory. Right now we are doing for scalar theory, free scalar theory, where O inverse absolutely does exist. So I don't think O inverse not existing usually means we can throw away the theory. It usually has there's some reason. There should be a reason for everything. So if something doesn't exist, we should look more closely at the theory and try to find out the reason. That's really the correct answer. Okay. So we got this. Now it's an easy exercise and notice, by the way, that this at the end of doing the differentiations, you're always left with a Z of 0, and we divided that. What was Z of 0? It was det to the minus half of O, but we don't even care as long as it's Z of 0 is here and here they cancel, but in particular it means that the determinant cancels out from this. So we don't need to know the determinant of O, but we do need to know the inverse of O. Now, given a differential operator, it's a lot easier to find its inverse than to find its determinant. And in fact, we'll see in this concrete example of a free theory, we'll see exactly what is O inverse. It's not at all hard to find. In fact, I'll do it now. So, remember that O was the operator I box x plus m squared delta x minus x prime. That's O of x and x prime. So what is O inverse? It's something such that if I take O of x and x prime and I multiply it with O inverse of x prime and x double prime, and I integrate over the common variable x prime, I should get delta of x minus x double prime. That's the definition of inverse. It's just like multiplying a matrix with its inverse and getting delta ij, just with continuous indices. And we know O. Well, the answer, I'll first write it down and then I'll prove it, is that O inverse of x and x prime can be written as an integral representation, d for k over 2 pi to the 4th 1 over k squared minus m squared plus I epsilon e to the I k dot x minus x prime. You've seen this quantity before. It's called the propagator of a scalar field, and I'm claiming that it is precisely O inverse, except I think as usual there's some sign, so this should be minus. So I claim this is O inverse. So how do I prove that? I put that over here, and then I act with O, and if I get delta of x minus x prime, then I'm good, then it's the inverse. Yeah, I never know whether these are things you've seen before or not. So this is something you know, you don't know? You do know. Very good. Okay, then we can do it quickly. So check. So this operator, so there has to be an I, this I and this I give me minus. So I'm trying to evaluate this quantity, O inverse. So I with I is minus, so I get minus, then integral. Then we have box x plus m squared acting on, this is the only place that depends on x, and divided by. Now box x, when it acts on this, I keep writing p, but it's k. Okay. When box x acts up here, it pulls out two factors of minus ik. So I get minus k squared plus m squared. So this is equal to minus of integral, same thing here, and then minus k squared plus m squared over k squared minus m squared plus I epsilon, and same exponential. And now we see that this is basically minus of that, so this minus goes, and I can make this k squared minus m squared. And now I can almost cancel these except for this I epsilon. So in the limit I epsilon goes to 0, I can cancel these two. But in fact, that I epsilon tells me that the integral d for k of that factor is exactly the delta function, delta of x minus x prime, x double prime. So what happened? I should have had, sorry, so good. So I'm trying to act with, so I skipped a few steps, sorry, you should have stopped me earlier. This is O of x and x prime, so this is correct. But there was a delta function which I skipped. I mean, this is all correct except by skipping a few steps. If you want to make up the steps yourself, then I can just skip them. Let's be complete and do it more carefully. So O is that, no objection. Now here we have O inverse of x prime and x double prime. And here we have box x plus m squared on delta x minus x prime.
And the integral over x.
And the integral over x, absolutely. Good. Now, I can perform the integral over x prime because it doesn't care about this operator, which depends only on x. And then this will set this x prime equal to that x. So I can forget the integral. I can call this x. Now I'm back where I was. This is the step that I had skipped. And now this one actually acts on the x dependence here and gives me k minus k squared plus m squared. And then that minus cancels this minus, and I get delta of x minus x double prime, which is the right hand side. So this is correct. So has an inverse, and the inverse is has this integral form. And it's something we already know. It's the so-called Feynman propagator in this case. So it's also called df of x and x prime, and it's called the Feynman propagator. So the 2-point function is the Feynman propagator. Of course, in canonical field theory, that's exactly what happens. The 2-point function, after a certain amount of work, turns out to be the Feynman propagator. And we've reproduced that over here. The main new thing being that it came just as the inverse of O. Yes?
So usually we put the plus I epsilon to talk about the
Poles, yes.
Here, how does it enter because I don't see any integration where
Yeah.
we need a pole stuff.
Yeah, the reason it enters is that the definition of delta function, or rather the formula which says integral over d for k of this phase is a delta function, is quite tricky because, right, I mean, this is a phase and I'm trying to integrate it over for volume. This phase always has modulus 1, so it doesn't look like it's going to converge unless I'm a little bit careful. And so if you look into the definition of this sort of integral d for k of a phase, you'll find that depending on the prescription that you give about how you define this integral, you can get various kinds of things, principal value and so on. And the particular one that gives you the delta function is exactly when there's an I epsilon in the denominator and k squared minus m squared up. I mean, you have to dress it up a little bit, but it's basically that. So this I epsilon actually assures you that the thing you're integrating leads to the delta function, which is exactly what we want. Okay, so this is done. And once we have this thing, then we simply can, now we can just erase this and do everything else much faster. So in the free theory, it's very easy to see that all odd point functions are 0. And the reason is, if I have an odd number of derivatives of that j O inverse j, then at least one j must be left behind downstairs, and I'm going to set j to 0, so that will go to 0. That's the calculational reason. Okay, what about the even point? So the really most important in a way is 4-point. It's kind of a basic object in particle physics because corresponds to, eventually by doing the proper correspondence between this and S matrix, we'll see that it's the case of 2 particles coming into some scattering and 2 particles going out. It's not yet that. Correlation function is not yet a physically interpretable object, but using it you can define the S matrix. That's another set of steps which I may not discuss here. But anyway, we can do this calculation and we get the very simple answer that it's the Feynman propagator x1 minus x2, Feynman propagator x3 minus x4 plus propagator x1 minus x3, x2 minus x4 plus the last one. And basically I'm differentiating that e to the j O inverse j 4 times, and it's basically the structure of differentiating an exponential which is bilinear in J 4 times, and then setting J to 0. And you immediately get this answer. And this has a nice physical picture associated to it, which I can draw, which helps me to remember how to write the answer in the general case. So if these are 4 points, don't think of any of them being in the past or future of any other point. As I said, that's a business for the S matrix to worry about, past, future, incoming, outgoing. None of that information is in this correlation function. I have 4 points. I'm supposed to join them up with propagators. Well, the options are I join this with this and this with this, then I get this term. Or I join this with this and this with this, then I get the next term. Or I join this with this and this with this, and I get the last term. So all ways of joining 4 points by a pair of lines and adding all those ways is the correct 4-point function. And this is the first and simplest example of the Feynman diagram procedure. It just says, instead of remembering to do this, you just make those dots, and then it's easy to remember that the final answer, in fact, one would prefer to write the whole answer. So with this labeling, remember that when you do this, you must never change the labeling. Whatever labeling you have picked in the beginning, you have to join this way, then you have to say plus that way, and then you have to say plus that way. The understanding is that the external points x1, x2, x3, x4 are all the same, the same in each, labeled the same way in each diagram. So the answer is this. And this answer is a function of 4 points. It has some properties. It's a little bit trivial. It also has some sort of physical interpretation. For example, if it were true that x2 and x3 were in the future and x1, x4 were in the past, then this might be interpreted as particle x1 from x1 propagates to x2, while the particle at x4 propagates to x3, but they never really interact with each other. Okay, and so we consider these to be non-interacting diagrams, and they are also disconnected. And disconnected diagrams are not something we really want, because if we want an scattering amplitude and a cross section for a physical process, then all the particles that came in should participate in that process. For example, supposing we had a system where 3 particles come in and 2 of them scatter, but the third one just goes out on its own, well, we would have already understood that process when as a 2-particle process. It's really a 2-particle process. The third particle is doing nothing. Or we could have a process where 1 particle for some reason splits into 3 and the other particle doesn't do anything. Again, it's disconnected, and I could as well focus on that particle which splits into 3 and ignore the one which doesn't do anything. So disconnected is something we would like to get rid of, and we will do it shortly. Now, we didn't get anything beyond disconnected diagrams, and this is not too surprising because we are working with a free theory. In fact, the reason to call it a free theory is that all its diagrams are disconnected. There are no connected diagrams. There is nothing which we can think of as a scattering. It's the same fact as the fact that we have a Gaussian, Lagrangian and Hamiltonian. Okay? Because once we have a Gaussian Hamiltonian, then at the end, the only thing in Z of J is J O inverse J, and that can only give you pairing of particles. There's nothing more it can give you. Okay, so it's a very boring result, but it's the basis for a series of interesting results. And it's about what we can say as far as free theory is concerned. For fermions, of course, I'm sure you know that there's similarly a Feynman propagator, which similarly its inverse, is the inverse of that Dirac operator, and it's known. You can look it up. That's simple. What's interesting is to now apply this knowledge to the interacting theory, and so now we are going to change our Lagrangian to be interacting, and all the features that we'll see are pretty much visible already for in a very simple example, which is where we'll take the interaction to be of 5/4 type. So we are going to put this into the path integral. Specifically for this thing that I have written here, you can see that the vacuum configuration is phi equals 0. So it's as good as before that I expand phi as 0 plus eta, and so I keep calling eta as phi, just like I did in the free theory. In the very next lecture on next week Tuesday, we'll choose a different potential which won't have a minimum at phi equals 0, and things will be quite different. We have just chosen this one to summarize the rules in the most simple way, because we don't want to spend our time worrying about a classical solution. Here the classical solution is very simple. So phi classical is again 0. So I want to emphasize that every time you see a Lagrangian, you need to think what is the phi classical. It's not automatic. Unless it's a fermion Lagrangian, then psi classical you can just blindly put to 0. It's just always 0. Okay, good.
So,
Yes.
the psi classical equal to 0 related to the fact that there are no constant
It
Rational
is.
number?
It is. But it's actually related to something a little more than that. For example, when we study, so supposing psi classical was not 0, what would it mean physically? It means that in our system, there is some kind of fermion sitting there, but that fermion, psi classical, is an, okay, so if psi classical was, okay, maybe I should not do this now. My point is that if psi classical was not 0, then I could have 1-point function for the fermion. But having a 1-point function for a fermion is a very bad thing, because that 1-point function, supposing, so question you can ask is, can I have this not equal to 0? Another question related to that is, can I, in a gauge theory, can I have this not equal to 0? Okay, and can I have a 1-point function of phi in some theory not equal to 0? We'll see. I think I'm getting ahead of myself because the next lecture is devoted to this question. So just take it as a preview. This is okay. We can rig up theories where phi classical is non-zero and therefore the expectation value 1-point function of phi is not 0. Just a way of saying it. But here what happens is, you see, if it's not 0, what is it? Psi is a spinner. It has a spinner index. Under Lorentz transformations, psi undergoes a Lorentz, some matrix multiplies it. This one also, some matrix multiplies it. But if it's not 0, it should be just some pure number. How can a pure number be multiplied by a Lorentz transformation matrix? Therefore, such expectation values would break Lorentz invariance, but this being a scalar would not. So I'm not going to explain this more now, but let's wait for the next lecture where I think these issues will come up. People do talk of, for example, 1-point functions, just to keep going in this incomprehensible direction. People talk of 1-point functions of objects like psi bar psi. Now the Lorentz indices are contracted, so though it's not a 1-point function, it's treated as a 1-point function because both these are at the same space-time point. So it's a single operator psi bar psi at x. This can be non-zero, and there's actually a very famous system where this is non-zero. It's called a superconductor. Okay, when you have a Cooper pair, it's a pair of fermions, and then that pair can condense in the vacuum, and the field theory representation of that statement is that the 1-point function of this thing is 0. Okay, maybe it's, I didn't say all the details exactly, but that's what it is. So this is just throwing that out for you to think about. But we don't want to allow any 1-point functions or classical solutions or condensates, whatever you call them, to violate Lorentz invariance. You could, of course, but then the result of our calculations would be non-Lorentz invariant, which would contradict the experimental fact that Lorentz invariance is true. Okay, all that for next time. Now we do something that we didn't do before. So first of all, we assume we have expanded S around this, but since it's 0, there's nothing to expand, so S is whatever it was. But now we break it up into S0 plus S interacting. And basically this is all quadratic terms, and this is all higher than quadratic. So in this Lagrangian, it's pretty clear. Let's assume that, let's write this as S integral of all this d for x. Then this much is S0 and this is S interaction. Now in the beginning of this first part of this course, you saw a variety of quite complicated field theories with all kinds of Lagrangians, and I leave it to you to figure out what is S0 and what is S interacting in those. For example, in a nonlinear sigma model, it's pretty strange because you have some Gij multiplying del mu phi I del mu phi j. Now that G will start with a constant and then it will have all powers of phi in it. We have seen examples. So the constant part of that is in S0, and all the higher terms will be like phi squared del phi del phi. Those are all of order 4 or higher. So those will all be in S int. So you have to physically break up S into two parts, the quadratic part and the interacting part. And the nice thing is now the quadratic part you can just treat exactly as we've treated before because it's a free theory. That's why we are making this breakup. So after this, you'll find that our Z of j, which we want to calculate, is integral d phi e to the I. Now it should be S of phi plus j phi, but I'm going to write this as S0 of phi plus j phi times e to the I S integral interaction of phi. Okay? Because I made the breakup, this e to the I S part factorizes into two terms, and I combine the j phi with S0. Is this clear so far? Now what do I know? I know how to treat this part if S int was not there, because this part is what I spent last lecture doing. This is quadratic, this is linear, we complete the square, we get j O inverse j, and the rest we have worked out today. This is the new thing which is confusing, and for definiteness today we'll just write the one which is actually there. So it is actually I minus lambda over 4 factorial. So maybe minus I lambda over 4 factorial 5/4 t for x. And S0 is the free theory that we have already studied many times. Okay. Now we want to calculate a correlation function in this theory, and the trick is very simple. So what do I want to calculate? I want to calculate d phi x1 up to phi xn e to the I S0 of phi plus integral j phi e to the I S int. Okay, so let me not right now introduce the specific form. I'll just keep calling it e to the I S int of phi. Okay. So the simple trick is, let's take this and make its power series expansion. It's an exponential. E to the x is summation of all powers of x to the n over n factorial. So this is the same as summation n equals, so now there's a new n. Be careful not to confuse my indices. This is m. M equals 0 to infinity d phi phi of x1, phi of xn. Okay, when I expand this, I'll get I to the mth power over m factorial, and then s int to the mth power. But I and m don't care about this path integral, so I can write them outside. And here I'm just going to write that. So first I'll write s int
So
of
J
phi.
shouldn't be there, right?
J should be there.
So this is the correlation function, right? Like not
Ah,
ZJ.
sorry. Good. So in fact, I want to calculate. Sorry. So I think thank you for pointing that out. What I want to calculate is Zj, and from Zj I know how to calculate the correlation function. So this is actually that is Zj. It's the same thing. I'm just trying to calculate that. Thank you. I was being a bit inconsistent. Differentiating in thing has not come yet. Okay. So I want to know how to calculate Zj in the presence of that that interaction. And so for that, I expand the exponential of the interaction. So here I have s int of phi to the m, and then I have e to the I s0 phi plus integral j phi. Now I notice a very nice thing. Now I am going to substitute s int to be the one which I already know, which I've already assumed, which is lambda over 4 factorial times phi to the 4th integrated. So this is lambda over 4 factorial to the m integral d for y phi 4th of y to the m. Okay, I think actually I should have followed
J
my
should
notes.
be there right now.
Yeah. So let's see. Yeah. So okay. I think let's do it the way I was trying to do it originally. I think I combined two things in a hurry. Let's just do it the way we should have done it. So we are not trying to calculate Zj now. Zj we already know. For the free theory that we'll use later. Let's say that right now we are trying to calculate our integral. Exactly what I wrote. No j, and then this. Okay. This is looking a bit better already. So it's this, and then I have to put the fields. Okay, now is everything okay? This quantity in the presence of interaction, I expand out the interaction, okay, and everything else is as it was before. And now again I'll take these factors out, so it's summation m equals 0 to infinity, I lambda over 4 factorial to the m, 1 by m factorial, and also these integrals. d4. So this whole integral is to the mth power. So in that term, what I'll do is I'll write d4 y1 up to d4 ym, and then this I'll write as phi to the 4th of y1 up to phi to the 4th of ym. But this has to be inside the path integral. All these things I've written till now are outside the path integral because they are not dependent on the function phi. Here I put phi. Then I put e to the I s0 of phi, then I put phi of x1 up to phi of xn, and phi 4th of y1 up to phi 4th of yn. Ym. Good. Everyone is with me. So, as you can see, the path integral is that of a correlation function in a free theory. S0 is the action of the free theory. We have the n points of which we wanted the endpoint function, and we have m additional points with 4 fields at each point, and we are supposed to integrate over those additional points, because after all the final answer should only depend on x1 to xn. So the thing that interactions have done for us is to introduce additional points, multiple fields at each point, and then integrals over all the points. But calculating this is the same as it was before by using del by del j for every phi in this product. You could even say that, well, these are phi's at n points. These 4 phi's, I'll break up this point y1 into 4 points. So there'll be 1 phi at each of them, and I'll do it for all of them. Then I'll do the del by del j trick. All the points will be distinct. I will have how many points? N plus 4m different points. So I have to do that many differentiations. And at the end, I'll combine all the 4 points into which I broke y1 as 1 point and integrate over it. So it's very tedious to say, but it's obvious what we are supposed to do. So let's now use this to get some formulae. Basically, we have re-expressed non-Gaussian path integral in terms of Gaussian path integrals. The price we paid is that it's no longer a finite set of Gaussian path integrals. We have to evaluate one for every m and then sum over all m's. Okay. Now this looks pretty hopeless, and it is hopeless. Nobody has, except in very simple cases, nobody has been able to carry out this sum. But this lambda appearing here gives us some hope, which is that each successive term has an extra power of lambda. So if lambda is a number less than 1, then this is a power series where the higher order you go in, the higher value of m you go, the more lambdas you have, and that contribution, whatever this whole thing which you are going to calculate, will be smaller by that factor. Okay, and so this is a perturbation series. And in fact, it's exactly the Feynman diagram series. I'll make a few general comments about perturbation series after I finish writing this out. So I have to rub this out now to make more space. Maybe I can write here. So the actual calculation of this starts by fixing an m and doing it order by order. M equals 0 we already did. M equals 0 means there are no insertions, and these things are done by Wick's theorem. Okay. So let's look at an example. Phi of x1, phi of x2, interacting theory. This will have its leading term, phi of x1, phi of x2 free, and we know that this is df, we've already said that. But now there will be the next term when m is 1. There's 1 power of lambda. These factors are just obvious factors, I over 4 factorial times m, which is 1, so it's just I over 4 factorial. But then, there's a minus that I think I lost on the way.
I.
Yeah, this should be minus. Good. So the next term is minus I lambda over 4 factorial times what? It's times phi at x1, phi at x2, phi 4 at y, integrated in y. So it's a 6-point correlation function of the free theory, where 4 of the points are collapsed to 1 and that common point is integrated. But you know, since we already have solved how to do n-point correlation functions, it can't be something so difficult. The only thing that could be difficult is carrying out the integration. What actually you get by evaluating the 6-point function is pretty obvious, And it becomes more obvious if you write it in the language of Feynman diagrams, because Feynman says to calculate this function, I'll mark my points x1 and x2, and I have a point y. Now, because there are 4 fields at y, there have to be 4 propagators coming out from here, and I have to join them in all pairwise ways between these 6 objects. So what are the things I can do? Well, one of them, which is a little boring, is to join this to this to this, and this to this. This is one option. You can imagine this y split into 4 separate points, and then you will see that these are actually pairwise lines joining those points. But then when I collapse the points back to 1, it becomes like a bubble. Okay, so this is one. Another one could be, now I won't keep labeling the points, this and this. Okay, so from x1 to y, x2 to y, and y to y. The general rule is everything must be joined by lines. Every line is df. So for example, in this case, the answer is df x1 minus y times df x2 minus y times df y minus, this is from y to y, so it's df of 0. df of 0 is not very nice, but it's something we can formally write down. As I said, evaluating these things is not necessarily obvious. So these are 2 of the possible diagrams, but there are more. Actually, there aren't more. I think to order lambda, those are all the diagrams. Can anyone think of more diagrams? I think that's it.
So there would be factors like you'll get multiple
Good.
of the second.
Of course, of course. So the point is, how do you get those multiples? This is a 6-point function. Treat it as a 6-point function, then there are no factors. That is Wick's theorem. It says just contract everybody with everybody in all possible ways. The factors come because 4 out of these 6 points are collapsed to a single point. So in my mind, there are 4 points here, and when a line comes out from x1, it has to attach itself to one of 4 possible phi's sitting here. That can be done in 4 ways. Then the line coming from here has only 3 ways left. So that's another 3 ways. So 4 times 3, 12. And then this has no choices left. So the answer is 12. But then there's also a 24 here. So you get minus I by 2. So that's how you count factors. This is all part of the subject of Feynman rules. It should have been done in QFT1, but in any case, it's something very standard in particle physics, and it's not the main thrust of this course. I'm trying to show you just that it can be reproduced. The Feynman rules that you already should have learned are reproduced by the path integral in a quite transparent way. It's simply the collapse of endpoint functions, some of which are interaction terms, many fields at one point. In this way, we see how the interactions really appear, and we see how the diagrams actually appear in a very clear way. And to order lambda, I don't think there are any more options, because think of it, the best way to think of it is to draw the empty diagram. So there's a line here looking to end somewhere, a line trying to end somewhere, and 4 lines from here trying to end. These are my 6 lines, which are the 6 phi's of the 6-point function. Now you have to join them in all ways. So if this joins this, then these have no choice but to join themselves, and that's the diagram I just erased. If this goes here, this can't come here, so it has to also go here, and then we have one more line, and it's that, and there are no other choices. So that's all the diagrams at order lambda. So therefore, this, we can say that this is equal to this plus this. And whenever this point multiple lines meet, we know that it's an interaction point and it needs to be integrated over. So its location needs to be integrated over. In actual field theory, when we do these calculations, we first go to momentum space where the propagator is simpler and we extract overall delta functions, and I'm assuming you've done all those things. Okay. At next order, we would have many things to take care of. We would have minus I lambda over 4 factorial whole squared. We would also have a 1 by 2 because it's second order in the expansion of e to the is interaction. Okay, so from that we get 1 by 2. This is 1 by 2 factorial. In every order of lambda, I'll have 1 by that. This is that 1 by m factorial where m is 2. And then I have my original points, they are always there. And I have two interaction points which I can call y1 and y2. So now m is 2. Now I have to join up 10 lines, 4 plus 4 plus 1 plus 1 in all possible ways. And I can get all kind of interesting structures. For example, now I could join this to this, this to this, this to this, this to this, and this to this. It's a disconnected diagram. Okay. Or I could join these here. This is a connected diagram. And probably you have learnt that this diagram, because there's one closed loop, it's called a one loop diagram. And this diagram has two closed loops, so it's called a two loop diagram. This is also a two loop diagram, but it's disconnected, so it's not very interesting. This one is interesting. This one is also interesting, and this arises at next order. And there's an entire set of rules about how many loops you get and how you get connected, how you get rid of the disconnected diagrams and all that, and I won't be able to do any of those things here. My purpose is to show you how the path integral gives this thing, and not really to work out this thing. I would say that if any of you plans to be a professional particle physicist, then learning loop diagrams from this stage onwards is very easy. All the basics are here, and then you have to really look into a book and find the set of rules for going to connected diagrams and so on. Now let's talk about human beings. You know, human beings have limited ability to calculate these diagrams, and the first real progress, although these diagrams came from the 30s when Feynman, Schwinger and Tomonaga wrote down quantum electrodynamics. In fact, it was more complicated because there they had two things we haven't even really discussed in depth: fermion propagators and photon propagators, which are more complicated. This is like a scalar version, so it's a toy theory which is much easier to actually discuss. A lot of features that they had to deal with are absent from here. For example, sum over spins, sum over polarizations, whatever it is. But anyway, at the time you could do by hand a one loop diagram. You can still do one loop diagrams by hand, they're quite easy. Two loop diagrams only for really tough people, and three loop and onwards is generally considered very hard for humans to do alone. But then, you know, already by the 1970s, there was assistance from computers, mainframe computers of that time, and now of course, basically when you want to calculate a Feynman diagram, you use a suitable package and you let your computer calculate it for you. Of course, you can't do it brainlessly because the computer will often find things which are infinite. You will have to tell it what to do with those infinities, and those things we'll come back to in the last part of this course. So that issue is renormalization. But I hope that this gives you a reasonably complete conceptual picture how the diagrams arise. The next question is how to evaluate and how to interpret the result. But how they arise? Simply by expanding the path integral after splitting S into S0 and S int. So it's very easy to see how they arise, and it's very easy to write down the diagrams that result from this, even, as I said, even though it's not easy to necessarily calculate. Any questions? Yeah.
So, when we do this using all our operator notation, we have to do certain, like going in the interaction picture. And all that.
None of that you
How
have,
does
yeah.
that- How how does it implicitly, like where does that?
Well, we split it. We did split S into S0 plus S int.
Right, but we never said anything about the scalar fields themselves, right?
True, exactly.
So, like,
Path integral is brilliant. This is an example of path integral's brilliance. We don't need to do any of that. You're absolutely right. We had to go into interaction picture. We had to worry about ordering of terms in the exponential and all that. But as you can see in a path integral, ordering isn't an issue. There's nothing to order. They are all numbers. They are all functions. The price is that you have to perform the path integral. But as we see, in this perturbation series, the performing of the path integral is solved by going to the ZJ representation, introducing a source, and then every phi that appears in your free correlation function is del by del J. Nothing more to it. It's easy conceptually. So it is, this whole process is actually easier than the operator version of the same process. But the price is, first of all, we had to spend many lectures learning path integral and also not getting scared by its really daunting features like this det to the minus half of O, which as you see we never needed it. And whether there are any hidden factors in the measure of the path integral, this d phi, whether this requires any, it had this strange limit we tried to construct very early in the course. None of that we needed to worry about, because whatever this is, as long as we assume the Gaussian integration rules, we don't need any more details about it. We just assume that this integral gives me det or det to the minus half, and then the denominator gives me the same det with any factors that might have been there, and they just cancel. And of course, the final answer just agrees with what has already been known for many decades before path integrals, coming from the canonical approach to field theory. So it's obviously right. And so things become easier and easier. Now the next step of becoming easier is when we go to fields like gauge fields, where gauge invariance is an issue, then everything to do with that is actually easier in this formalism. Also, if we go to systems with global symmetries, which we discussed earlier in the course, we may want to know what is the impact of those ON or UN type of symmetries on the correlation functions. That's also something that in path integral is fairly transparent. So many things become transparent from here on. And one of the things famously very conceptually confusing is the issue of spontaneous symmetry breaking, which we are going to discuss next Tuesday. It also has its simplest expression in path integral language, because here what we'll see is that the phenomenon of spontaneous symmetry breaking and then also the Higgs mechanism all come because we have to evaluate a path integral around a classical solution, and we will realize that sometimes the classical solution isn't phi equals 0. So next time that's what I'll do, classical solution which is not phi equals 0. We'll also see that if you do things with a classical, if you choose phi equals 0 as the classical solution, though it's not a good solution, you'll get somewhat nonsensical answers. So we'll learn that choosing the classical solution wisely is important. So just to give you a preview, if I have a potential like this, this is the value phi equals 0. And you see that it's not a local minimum, but it's a local maximum. And maximum is a bad place. So when I said that at past infinity phi should go into the vacuum, you cannot imagine that this is what it means for phi to go into the vacuum. You should think of this potential as a kind of physical object with a ball rolling, some dot which is rolling. Well, the ball is certainly not going to come to rest there. It's going to go either here or here. This isn't a vacuum at all. It's just not a minimum. It's a stationary point, all right. So it satisfies equations of motion, but it's not, it's not physically a vacuum. And all the confusion about this class of theories comes if you assume that this is a vacuum. Then you will come to wrong conclusions. When you realize this is a vacuum, you will come to correct conclusions, but they'll be quite subtle. So that's all for next time. Any questions?
What conclusions are wrong, like taking?
We'll see next time. Everything will be worked out next time. You'll see exactly what conclusions. If you want a preview, the fact that the mass of the particle will apparently be imaginary. That doesn't look nice. That would be the fault of us choosing that as the classical set.